Okay, class, welcome to lecture 26. Today we're going to talk about relations. So the idea for now that you want to be picturing for these guys is we studied functions and we were able to draw these pictures of functions, but there were like these rules that had to happen for something to be considered a function from A to B. So for example, something like this is perfectly acceptable as a function, but there were lots of things that were not functions. So something like this is not a function for two reasons. One, because this guy is getting assigned to two different elements. For one, that's bad for functions. And then for two, this guy is not getting assigned to anything. So a function can't do those things, but these are still worth studying anyway. These types of pictures, they are interesting for different reasons. So we're not just going to throw them away. They're not functions, but they are something else, and they are worth studying. So that's what we're going to study next. Okay, so this is the definition that we're talking about. A relation. So the idea is that a picture like this creates relationships from one set to another. That's where this name is coming from. So like the dots that are connected are related, the dots that are not related. So a relation, instead of a function, we're going to denote it with a capital R from a set A to a set B. Now the definition is going to look a little weird, but this is what it is, and then we'll explain how it works with the picture. Is actually a subset so it's sort of weird. We call the relation R, but then we also call the subset that it creates R. Sometimes we won't do that, and we'll see later, but we do sort of reuse this. And we're going to reuse the letter R a third way. It's kind of annoying. Okay, so what is this subset? It's a subset consisting of ordered pairs living in A cross B. So remember, the product of sets consists of all ordered pairs. So these are just some of the ordered pairs. Which ordered pairs? Well, the ones where A is related to B, which we write as ARB, like that. So it's a subset of the whole product because it's just some of them, some of the elements in the product, but which ones depends on the relation. So the way you read this is you say A, you could say A is related to B. If you want to say it out loud every time, or just ARB, literally just say the letters. So the relation is the subset consisting of ordered pairs where the coordinates of the ordered pairs are things that are related. And if something is not related to something else, it won't be in this set. Okay, so this example is, or this definition is sort of tough to grasp all at once, but what we need is an example. So let's see, what do we need to make an example of a relation? Well, we need a set A. So of course, we'll start with some smaller sets before we move on to crazy stuff. We need a set B to go to. So I don't know, X, Y, and Z. So now we're going to create a relation from A to B. So you can create whichever one you want. I'll make one. So the relation just has to have ordered pairs in it. So I'll just stick some ordered pairs in here. How about 2 comma y. So the first coordinate does have to come from A. The second coordinate does have to come from B. So it's got to look like something like that. 2 comma y. How about 2 comma z? How about 1 comma x? And I don't know, 1 comma z, something like that. So these 4 elements can create the subset of A cross B. So we say that this is a relation. There are many relations. This is one. So this is one from A to B. So just to practice using this notation, so what elements are related to each other? Well, 2 is related to y because 2 comma y is in there. 2 is also related to z. 1 is related to x, and 1 is also related to z. So what we can sort of see already happening is how it sort of looks like a function, because you can sort of think of this as like an assignment. So notice that a relation is similar to a function, because what we're still doing is we're sort of assigning elements to elements, because we're assigning in this weird way. So you could sort of think about it as, in terms of these pictures, 1, 2, 3, x, y, z, where it's not a function because the assignment doesn't obey the rules of a function, but it still is an assignment where now I'm saying that 2 is assigned to x, but now it's, sorry, y. Couldn't remember what I wrote up there. So 2 is related to y, but it's also related to z. And so you can think of it as being assigned to both y and z, which is not okay for functions, but is okay for relations. Meanwhile, 1 is related to x, and I think it was, z. So it's still an assignment from A to B, where you can have less restrictions. It's a less restrictive way of assigning. Functions are lame. They got all these rules. But relations, you do whatever you want. Make whatever relationships you want. Functions are mean. Relations are cool. Okay, so what this also does, this sort of shows how functions create relations. Because the idea is that a relation has less restrictions than a function. So if I happen to have a function where I impose these rules about what can go where, or whatever, it still creates a relation. But it's just a relation that also happens to be a function. Okay. So for example, just do another one here, using the same sets as before. So this guy is both a function and a relation. So you might write something sort of very strange. You would say like f goes from A to B because it's a function. And you might also say, well, it's also this weird relation. So I can also say something like this. as a relation, it consists of the pairs that you get from the assignment. So you get 1 comma y because 1 goes to y, 2 comma y because 2 goes to y, and 3 comma z because 3 goes to z. Okay. So in function notation, you would say stuff like this. But for relations, you would say something like on the right. Okay. So in fact, this always works. So a function always, doesn't have to be a small set like that, always creates a relation. So here's how. If you have an arbitrary function from a to b, then the relation way of saying that function, well, the ordered pairs that you get are really just what you plug in and what is outputted. So the way to say that arbitrarily is a comma f of a, or a is an a. So these ordered pairs form a relation that comes directly from the function. Okay, so in any case, functions always create relations, but not vice versa. So relations are better. They're less restrictive, and you can make more of them than you can functions. Okay, so let's think of other examples that are not related to functions and that are not just like me drawing pictures that create relationships. So here's another one. Greater than creates a relation from R to R. You can also do from Z to Z or Q to Q if you want. Where when are two things related? So X is related to Y when X is bigger than Y. So when you have a symbol that already tells you the relationship, it sort of becomes silly to keep using R. So very often we won't later on. Okay, but in any case, I'll still use R for the set because the subset, because it just looks too strange to use the symbol greater than to name the set. So I cannot do that. It just looks too strange. Okay, so we're gonna keep using letter R in this example. Whereas up there we used F because it didn't look that bad. All right, so what is the relation? So it's got to be a subset of R cross R, real numbers cross real numbers. And so it consists of ordered pairs that live in R cross R, first of all. But which ordered pairs? Well, just the ones that come from the relationship. And now I have a specified relation, so I can actually just use that instead of saying X, R, Y. So this is the relation you get from greater than, from the greater than symbol. So just for little mini examples, you should say like what kind of elements it has. So like what is in here and what's not in here. So like 1 comma 0 is in there because 1 is bigger than 0. -4 comma -7 because -4 is bigger than -7. 10 comma 5, stuff like this. But not things like 2 comma 7, right? Because 2 is not bigger than 7. Also 2 comma 2 is not in there because 2 is not bigger than 2, it's equal to 2. And stuff like this, right? So -3 comma -1 because -3 is not bigger than -1. So in fact, we could sort of sketch a picture of this relation because it lives on R cross R, we can draw it. So what is it really? Well, it's all the numbers to the right of the line y equals x. Sorry, all the ordered pairs to the right. So you might just draw something like this and shade it, not including the ordered pairs on the line, because that would be when y equals x. If I just changed greater than to be greater than or equal to, then I would include the line too. Okay, so that's the relation. All right, so greater than is a relation. Here's another relation. It just looks like a line, but it's supposed to be divides. Divides is another relation. But it's not on the real numbers because you never talk about divisibility with the real numbers. You only talk about divisibility with the integers. So it's really a relation just from z to z. So how is the relation built? Well, the divides is what creates the relation. So what we're going to do is the same as before. You just say, when are two numbers related? Let me use m and n though. When are two numbers related? If m divides n. So what does the relation look like this time? Well, it looks like all the ordered pairs of the form m comma n that first of all live in z times z such that m divides n. So again, it doesn't hurt to just list some elements just to see if you can notice any sort of pattern. So for example, 2 divides 2, everything divides itself. 2 divides 4, 2 divides 6. So that creates an entire list of things as you can see the pattern going. I don't know, 5 divides 10, 5 divides 15, and so on like that. And then there's also negatives in here. So like negative 4 divides 4. Oops. So that's in there. Negative 4 divides negative 4. Oops, I keep doing that. So that's in there too. Lots of stuff's in here. Lots of elements. So let's say some stuff that's not in here, but not. Well, for example, 7 does not divide 10. But perhaps more interestingly is things like this. So just because 5 divides 10 does not mean 10 divides 5. So very often you'll have a pair where the opposite pair is not in the relation. So a relation sounds like a two-way thing. Like if I'm related to you, you should be related to me, but that's not necessarily true. We can see right here, 5 is related to 10, but 10 is not related to 5. So in general, a relation does not have to have the property that if one thing is related to the other, then that is related to the first thing in the other order. Okay, so that's sort of interesting, and that'll come up later too. Okay. So now what we're going to do is we're going to define a completely new relation. A new relation still from z to z. It's a relation that's very important to mathematics, and you'll see it a lot if you keep learning more math. So it's called congruency mod n. So this means this is read as congruent. So congruent mod stands for modular and then the number n. But you just read it as congruent mod n. That's how you say this phrase. Okay, but we'll say it more when we practice with it. So here's how this relation is defined. So I need to define when two numbers are related to create a relation. So here's how I'm going to define it. I'm going to say that two numbers are related when their difference is divisible by n. So that's the same n as this n here. So it seems a bit weird at first, And then the way we use the symbol when this does happen, so if A is related to B, we write that A is congruent to B mod N when two things are related by this relation. Okay, so let's just go through examples, much easier. So what happens is we get a different relation for each n. So we're also going to pick an n just to start to see a more specific example. So for example, if I use 6, I'll get a certain relation. And if I use a different number, I'll get a different relation. Okay, so if I use 6, I'm saying that A is related to B when 6 divides their difference. And then you write, when this happens, that A is congruent to B mod 6. So let's think of examples of things that are related to each other. So for example, 10 is related to 22 because if I do 22 minus 10, I get 12. And guess what? 6 divides 12. So what we can write is that 10 is congruent to 12 mod, sorry, 22. I changed it to 12 for no reason. 10 is congruent to 22 mod 6 is a thing that we can write. It's true. So that's one element in the relation. 10 comma 22 as an element among many other elements. So something that's not in here would be like 22 and 11, because this is 11 and 6 does not divide 11. So you would say that 11 is not congruent to 22 mod 6, for example. So 11 comma 22 is not an element of this relation. Okay, but in this example, we're going to actually try to organize our thoughts a little bit better and try to list all the, sort of be able to classify all the elements that we can, that there are in this relation. Okay, so let's think, try to understand elements in this relation in general. Instead of just randomly picking numbers and seeing if it works or not, let's try to do something better. So here's how we'll do it. So first you have to notice, or I guess I'll just tell you to notice it. That's the shortcut, as I just tell you. So 0 is related to 6 because 6 minus 0 is 6, which is divisible by 6. But then if I just keep doing multiples of 6, those are all going to be related for the same reason. Mod 6. And it also goes for negatives too, so you could go backwards this way. Negative 6, negative 12, and so on. And I can actually prove this very quickly because a multiple of 6 just looks like something times 6. So this is really because a multiple of 6 minus another multiple of 6. So I'm not formally proving it, but I'm trying to give you some evidence here. You could write this into a real proof. A multiple of 6 minus another multiple of 6 is a multiple of 6. So 6 will always divide the difference of two multiples of 6. So all the multiples of 6 are related to each other. And so for example, 6 comma 12 is in R, but also I could subtract the other way and all that's going to happen is I'll get a negative. So in fact, 12 comma 6 is also in R. And that'll work for any two. So in fact, 6k comma 6m, those are all in the relation for any k and m that you pick in the integers. So 12 is related to 18, 18 is related to 6, negative 6 is related to 6, backwards and forwards, it all works out nice. But there's actually something even deeper going on here. So this is saying that all the multiples of 6 are related to each other. But also, if I start at 1 and I count by 6, the same pattern will happen. So 1 is going to be related to 6. Sorry, I have to count by 6. So I have to get to 7. What's 7 plus 6? 13. This is the hardest part of this stuff. I forgot how to add by 6. 19, and so on like that. These guys are all going to be related. Also in the other direction. So what's 1 minus 6? Negative 5. These are all related. And for the same reason, well, these are not multiples of 6 anymore, but they all look like 6k plus 1. So if I take the difference of two guys like this, oops, they're different letters, then what happens there? Well, the ones will cancel. So I'll still get a multiple of 6. So then the point is that 6 will always divide a difference of these two kinds of numbers, where the two numbers just differ by 6, but that's it. Plus 1, sorry. Okay, so in general, 6k plus 1 comma 6m plus 1, those are all in the relation 2 for any integers you pick. So 1 is related to 7, 7 is related to 13, 13 is related to negative 5. All those numbers in this infinite list are related to each other, and either one can come first, because if you just subtract the other way, it'll create a negative. So it still works out. Okay, and then this pattern just continues. Meaning, now I'll start at 2. 2 will be related to all the numbers I can get by just adding 6s. So 8 and 14, and so on. 3 will be related to 9 and 15, and so on, both directions. 4 will be related to 10, 16, and so on. And then luckily I'm not going to go forever. I'll just do this last one because it is the last one. Because what happens when I get to 6? Well, I already did that actually, because that's included already in this list. So the pattern continues, meaning these numbers just look like 6k plus 2. These numbers just look like 6k plus 3. These numbers just look like 6k plus 4 and 6m plus 4. And these numbers just look like 6k plus 5 and 6m plus 5. So all the numbers of these forms, all the ordered pairs of these forms, are all also in this relation that we've created. And that's the idea. So if we just pick a different n, we'll get a different relation. Let's pick a smaller one. And we'll notice that whatever n we pick, that's how many sort of lists we're creating. So this guy, actually, there were 6 different lists. There's these 4 and then the 2 I did before. If I pick n equals 3, they're just going to be 3 lists. So let's start from scratch, though. So if I pick 3, then what I'm saying is that A is related to B when 3 divides their difference. And then we write, when that happens, A is congruent to B mod 3. So same exact idea happens. All the multiples of 3 will be the same. Because if you subtract 2 multiples of 3, you'll get a multiple of 3. But then if I sort of start counting by 3s, but I start at 1 or I start at 2, then I'm going to get 2 other lists of things that are all the same. Oops. It's 1 minus 3, negative 2, 2, negative 1. So same idea there. These are all the same mod 3. These are all the same mod 3. These are all the same mod 3. They're all congruent mod 3. So these guys are all congruent mod 3. These guys are 2. And these guys are 2. Because their differences will always be a multiple of 3. And you could check, pick any number you want on this list. Pick like 11 and pick negative 1. If I subtract them in either order, that will be divisible by 3. And so what this is saying is the things that are in this relation are things of the form 3k comma 3m, 3k plus 1 comma 3m plus 1, and 3k plus 2 comma 3m plus 2 for any k comma m in the integers. So that tells you every single thing that's in R, this little piece of information. Okay, so this is very related to clocks, actually. So let's think about that. So this relation relates two numbers. Another way to think about this, when they are the same on a clock with n numbers. So how do we think about that? Well, pretend I had a clock that only had 3 numbers instead of 12 numbers. So I guess I would draw it like this. So then, as it goes around, you would say, oh, it's 1 o'clock, but then it goes around once, then you would say it's 4 o'clock. And that's just the same as saying that 1 and 4 are the same mod 3. So a clock with 12 numbers, an actual clock, you may have noticed this pattern. In military time, people might say 13 o'clock, but that's because 13 is the same as 1. So other people would say 1 o'clock on a clock with 12 numbers. Okay, so 2 would be like the same as 5 if you went around, and so on like this. Okay, let's see what else. So one other thing that people do with this mod stuff, they do lots of stuff, but one more thing I'm going to talk about. So people also just write the numbers that are congruent to each other in lists. So they sort of forget about the fact that there's this whole relation business going on where you have to write ordered pairs when two things are related. Instead, they might just do something like this. So for n equals 4, then what you're saying is that 2 numbers are congruent when 4 divides their difference. What this does is this divides the integers into 4 subsets. And those subsets just come from listing all the numbers that are related to each other, mod 4, that are congruent to each other, mod 4. I'm sorry, there's a hair on my screen. Get away. Okay. All right. So what I'm saying is there's all the numbers that are congruent to 0. There's all the numbers that are congruent to 1. There's all the numbers that are congruent to 3, or sorry, 2 is next. And then there's all the numbers that are congruent to 3. And these 4 contain all the integers, because what this first set is saying is it's saying list all the elements that are the same as 0, aka that are related to 0 in that relation. So those are all the other multiples of 4. And then this one is saying list all the guys that are related to 1 by that relation. So that would be 5 and 9, just by adding 4s and subtracting 4s. You get all of them. And now all the guys related to 2, mod 4, aka all the guys related to 2. And now all the guys related to 3. So notice that none of the lists have any overlap, but together, if I union all 4 of these together, that would get me the entire integers. Okay, so blank congruent to blank mod n is a relation, that's what we're talking about. It creates a subset of Z cross Z, but it's extra nice, which means it has extra properties. So we already sort of noticed one, which is that if A was related to B, then B was related to A. Oops, not the real numbers, the relation. So that happened up there. For every pair that's in the relation, you can also find the pair in the reverse order in the relation. So that's one extra nice property. Another nice property is that every single number was related to itself. That's what this is saying. So these are 2 nice properties we're going to discuss next. We're going to formalize them, but I just want you to think about it in the context of what we did up there. So like when we did mod 3, for example, 1 was related to 4, but also 4 was related to 1, and that was true for every pair of numbers, because you can just, if you subtract in the opposite direction, you'll just get a negative, and if something divides a number, it also divides the negative of that number. So that's why that's happening. So this is just an example of that, this nice property. The other nice property was, well, I guess I didn't explicitly say this, but this is always true for every integer, positive and negative, because if you do 1 minus 1, you get 0. 0 is divisible by 3, and this will always get you 0, this process, so 3 will always divide the difference. Okay, so these 2 nice properties hold, but now let's name them. And play around with them. Okay, so this is a property of a relation. So I have to, first of all, have a relation R from, well, these relations are already especially nice because they're going to go from a set to itself, from A to A. To be able to do this stuff, you have to go from a set to itself. So is called reflexive. This is the first property. If for every element of A is related to A. So one example of a relation that is reflexive, very quickly, besides the one we just did, is equality of numbers. So equals is a relation from R to R. So first of all, it goes from a set to the same set. And when are two things related? When they're equal. So the only time two things are equal is if they're the same number. So this guy really only consists of x comma x. And so we can see why it's reflexive, because it's almost built to be reflexive. So this is a reflexive relation because no matter what number you pick in the real numbers, A comma A is definitely an R, because yes, A does equal A. And you could write A, you could write that, or you could say A is related to A. Either thing is fine, it's the same. This is annoying me because this is R, not the real numbers, sorry. This one's the real numbers. This is the relation R that you get. Okay. So every number is equal to itself. So that's why equals is a reflexive relation. So let's see something that's not reflexive. How about greater than? We looked at that earlier. It's not reflexive. Just very quickly, well, because 5 is not bigger than 5. In fact, x is never bigger than x. But I only really need one counter example. So x is not related to x under this relation. Still a relation, but it's not reflexive. Okay, so then the last definition for today is the other nice property of that a relation can have. So a relation is called symmetric. So I guess I do have to say all this other stuff. So relation R, whoops, from A to A, it's called symmetric when, whoops. So I want to be very clear right here that this property is an if-then property. Whereas up here, reflexive is a for all property. So to be reflexive, every single A has to be related to A. Over here, symmetric is going to be an if-then property. So you just have to check that the conclusion follows from the hypothesis. So you're not worried about when the hypothesis doesn't happen. Okay, so here's the definition. If A is related to B, then B is related to A is true. So to be symmetric means that whenever you have, so first of all, this has to happen for you to check this property. Whenever you have something related to something, it's also true as a result of that the relation holds the other way. Okay, so it's an if-then property. So what that means is, just as a quick example, if 5 comma 6 is in R, then 6 comma 5 better be in R also. But if something is not in R, like 10 comma 7 is not in the relation in the first place, well, then we don't care if 7 comma 10 is in R, because the hypothesis is not fulfilled of the if. So we only care that the then follows from the if. We don't care. I did not say for all A comma B. If it was only symmetric for all A comma B, then yes, this would always have to be true for all A's and B's. So you would have to check that it has every single element, which I guess would be ridiculous anyway, actually, because relations wouldn't typically have all of the possible ordered pairs, because then that would just be the whole product set. So yeah, it's an if-then statement. Okay. So just a very quick example. Equals is again symmetric because if A equals B, then it's true that B equals A. So if A is related to B, then B is related to A. Always happens just by the definition of what it means for two things to be equal. Okay, so something that's not symmetric is greater than. So for example, let's do a little counter example. 5 is bigger than 3, so I'm satisfying the hypothesis. I found that 5 is related to 3, but 3 is not related to 5. 3 is not bigger than 5. So it's not symmetric because I found a situation where the hypothesis satisfied, but the conclusion did not follow that I wanted. Okay, so now we'll do sort of a more contrived example, but it sort of helps us see what's going on a little bit better. So in this example, I'm just going to create a relation from a set. So here's a set, 1, 2, 3. And R is the relation from A to A. So I'm just going to define my own relation, not use like equals or greater than or something. I'm just going to make up my own ordered pairs. So I'm going to say 1 is related to 1, 2 is related to 3, 3 is related to 2. That's my whole relation, just those 3 ordered pairs. And of course, you could try to draw a picture again if you want. 1, 2, 3, 1, 2, 3. So saying 1 is related to 1, 2 is related to 3, 3 is related to 2. Okay, so this relation, let's see, do we think it's reflexive? This R is, it's not reflexive, but it is symmetric. And we can check this real quick. So reflexive is a for all property. So I need to say that for every element in A, I need to check that A comma A is in the relation, i.e. A is related to A. But it's not true because only 1 comma 1 is in there. Only 1 is related to 1, i.e. 1 comma 1 is in the relation, but 2 is not related to 2. So 2 comma 2 is not in the relation. So it's not happening for every element of A, it just happened once. So it's not reflexive. 3 comma 3 is also not in there, so it's another reason it's not reflexive. 3 is not related to 3. You need to have every element related to itself to be reflexive. Symmetric, again, it's an if-then. So I have to look at each guy in here. I only worry about the ones that are actually in there and see if their reflection is also, their ordered pair that's the opposite, is also in there. So this guy is yes, because whenever this happens, this happens. So let's check the, let's look at each time the hypothesis is satisfied and see that the conclusion follows. So 1 comma 1, that's an R. 2 comma 3, that's an R. And 3 comma 2, that's an R. So just again, that's the same as saying 1 is related to 1, 2 is related to 3, and 3 is related to 2. So if I have something in my relation, is the opposite one also in there? Yes, in the first case, because 1 comma 1 R1 is the reflection of 1 R1. So that conclusion follows. Okay, so if I start with 2 comma 3, is 3 comma 2 in there? Yes, 3 comma 2 is in there. So 3 is related to 2. And if I start with 3 comma 2, is 2 comma 3 in there? Yes, it is. 2 is related to 3. So R is symmetric. So in this sort of contrived example, I'm just like literally checking every possible case. Okay. But that's not so hard because I can check every time the hypothesis holds. Every time something is related to something else, I can check manually if the opposite is true. Okay, so that'll be it for today. We're going to do a little bit more on this on the next lecture, but I'll see you next time.